Hi, I'm John Anderson, and this is Enhanced Content for Common Engineering and Technology courses, Module 6, the second of two parts of the Introduction to Composites. So, last time we talked about the materials that go into a fibrous composite and sort of introduced the concepts. This time, in this module, what we want to do is talk about how we combine those materials so that we make an actual composite part. So we'll go through the basics, probably the most basic composite manufacturing technique, which is wet layup, and then some modifications on the wet layup. And we'll, as part of that discussion, I have a couple of videos I want to show. One is from I found on YouTube, which is a really interesting basics of wet layup that talks about some of the parameters for the basic concept of wet layup. And then there's a short video on how fuselage sections for the Boeing 787 are actually built. So I hope you enjoy this. Again, this is Module 6. So the basic process for building composite parts is shown in this diagram on the lower right hand corner of our slide. We start out with a laminate. That is, we take our fibrous material and we put it into layers, stacks, as we talked about in the last module. Then after we place these stacks in a mold to give us the shape of our part, we put a vacuum bag over the top of it, as we discussed, and then we apply heat and pressure. The vacuum bag at the top pulls down because the pressure inside the bag is lower than the atmospheric pressure, so it pushes down on the top of the part and consolidates the part, or pushes gases and excess resin out of the fibrous material so that you get a void-free part. And it also helps it conform to the mold. So we apply the vacuum and we pull this down. For some parts we're going to actually apply an external pressure also in addition to the vacuum. And we'll apply heat. The heat allows this cross-linking or curing of the resin material, the matrix holding these fibers together, to proceed at a faster and more complete rate, or faster rate and be more complete, I should say. So after heat and pressure, we allow this to sit, sometimes at a lower temperature, again making sure that we've had the reaction, the cross-linking reaction in the resin go all the way through to completion. And then we demold and we have the cured part. So in some way we need to combine the fibers with the matrix, or actually put the matrix onto the fibers. And there are several ways that we could do this. First of all, we have to arrange the fibers, and so usually we take a fabric and we cut it in the shape that we want, and we put it into a mold. Now this mold that's shown here is a female mold. That is, the walls of the mold will define the exterior part, the exterior of the part itself. So the walls of the mold also define our surface quality. So we'll lay the sheets of fiber or cloth into our mold, and then we'll somehow get the resin onto the fibers. So the first step in all this is to get our plies, or our layers of woven material, woven fibers, into the proper shape, the geometry that we need to fit in our mold. So if you're making one part, you could probably just hand cut the fabric, trim it so that it fits the mold well, and it's all good. But if you're doing multiple parts, that you want to conserve the material as much as possible. That is, you're making 100 parts, and so the material wastage becomes a factor there. You want to do something different. And one of the common ways that's done is with a CNC cutting machine. So we'll lay out a pattern on the CNC cutting machine, the computer numerical control cutting machine, that's the most efficient pattern that we can cut out of this width and length of cloth that we have. And then the machine automatically cuts that. Now, this, interestingly enough, was this machine is also used in the garment industry to cut out patterns of cloth to make garments. So the wet layup. Basically, the wet layup process is we lay the fabric in the mold, we saturate the fabric with a mixed liquid resin. Most of these thermoset resins are two-part resins. That is, we mix two chemicals together, and that starts the chemical reaction. So once we mix them, we have an open time for the resin, because the reaction has already started. And over a period of time, this resin, the mixed two-part, will start to thicken and eventually harden. So our challenge here is to mix the two parts of the resin and quickly go and saturate the fabric when we have a low viscosity liquid that will get into the pores in the fabric more easily, or wet out the fabric as the terminology is. So we work the resin into the fabric so that it conforms to the mold. We add another layer, another ply of fabric, and we repeat the process with the resin, and we continue until all the plies are in place, and we work the excess resin mechanically out to the edges, and the composite conforms to the mold. Right now I want to show you a video of actually this wetting out process. It's about a 5-minute video, so let me turn that on.
We'll take some of the fabrics and we'll just wet them out with epoxy, get a feel for the different fabric types, the input between Kevlar, glass, and carbon, and we'll try to get a feel for how the different weave styles affect how well they wet out with epoxy. And what we have is carbon uni, we've got some Kevlar woven and some glass woven, and some 1708 knitted glass, and some 1.5 ounce chop strand mat. So we'll do those, and then we'll wet out. And this example here is a stack of 4 plies of each of those products, and then we're going to put a peel ply, which is the blue material, on top of those. Just squeegee out the fabric and put the peel ply on top, and try to consolidate just by hand, no vacuum pressure, but just by hand. Consolidate the laminate, get all the air out, make a nice solid laminate of these fabrics.
Part of the key to that is just to get a good wet kind of edge with the brush, ahead of the brush stroke there. Really what you're trying to do with the brush, push the resin into the bundles. So you've got resin coming up and you've got resin going down.
So I think the thing to notice here is that the cloth really wets out fast with epoxy. It's just, cloth and epoxy are just made for each other. And you know, you can see that this epoxy is cold, it's thick, which is really not the best situation, but even so, it just wets out beautifully. You can also see that the cloth is really hard to keep in line. It's a cloth, so it doesn't, you know, it's not woven, it's not stitched, it's not mechanically attached together, it's just together by the weave itself. And then when we're done with that last layer, we're just going to put a layer of the nylon peel ply. That's the blue material. That's just going to give us a nice, smooth surface on the top.
And what's in there? Is it just the nylon itself?
The nylon combined with the blue material, which is a silicone additive or vinyl ester. And so when we're done, we'll be able to peel that off. And we'll have a nice kind of slightly abraded smooth surface on the top. And whatever finish you have on the top of the peel ply, you will get to the top of the lanyard. So it does, if you're concerned about that, it does benefit you to take some time just to squeegee out those little wrinkles.
Well, will some of the ME blush go away?
Yes.
Yes.
There's a difference between wetting out glass and wetting out Kevlar. It's just,
harder.
it's a lot more difficult to feel comfortable doing a good job. And, you know,
And that won't mechanically stand up when you get done, even with a peel
Yeah,
bar.
it's a disaster.
but you can peel that back and you can see that the combination of having the substrate, the table pre-wet,
Yep.
and ensuring that you've got a lot of resin there, you know, that's how I feel comfortable, knowing that you've got Kevlar properly wet out. Obviously, there's more resin than you need, but I'd rather be on the safe side than Kevlar. This is actually an infusion resin that we have in the shop. It's very, very thin, as you can see, but it's a vinyl ester blend, infusion resin. It's a very nice resin. Now, what we could do maybe at the same time is just take the epoxy and do this exact same thing I'm doing with the mat. Just wet that out and then do it side by side. You can see how the mat just really disappears with styrene-based resins. I mean, it's just really, really clear. The binder that's holding the mat together is designed to dissolve in styrene. And the problem is, or the good news is, that epoxy has no styrene in it. So we put that on here, we're doing these side by side, and you'll really see how one just wets right out, and the other one doesn't. See, it looks like it's dry, but it's not. There's plenty of resin. It's just not breaking down the, it's just not breaking down the binder.
Anyway, that's pretty much it, I think.
Okay, so in the video you saw fabric just being wetted out flat on a table. So if we want to put contours, we want to actually make a usable part, we have to have a mold. There are two types of molds, as I said. There's female molds, as you see on the left, and there's male molds, as you see on the right. Actually, this is a female and a male. You have a female cavity here and a male part here. Typically, a male mold would be something that you lay up the fabric around the mold, and then the interior of the part, the composite part, has the finished surface on it. Now, wet layup is probably the simplest methodology, but the problem is you get a lot of wastage there. Well, you get a lot of wastage, and it's very hard to control how much resin you have in your finished product. For the highest performance parts, what we'd like to do is have the minimum amount of matrix material necessary to hold the resin in, or to hold the fibers in place. The resin or the matrix material has a much lower strength than the fiber, so we want to have most of the weight of our part be fibers and a minimal amount of resin to hold it in place. We also have the issue of we want to only put just enough resin in place in order to make the part. We don't want to waste any resin. So you can see from the video and the description we've had, the wet layup process is not very economical in terms of resin. A way around this, a solution to this, is to have a pre-preg material. Pre-preg is an abbreviation for pre-impregnated fabric. So what we do is we take this fabric and we coat it with a resin material. We impregnate the resin material in it in a controlled fashion, and then we take this, and the resin is already activated, that is, the two parts have been combined. So we lower the temperature, and the lowering of the temperature retards the curing or the cross-linking process. Remember that in the overall process description we talked about heating the material to facilitate that cross-linking. Well, the opposite is true. If we lower the temperature, we can retard that cross-linking. So now we have these sheets that have both the fibers and the resin in a very controlled volume of resin, and we can put these in a refrigerator, keep them for a certain period of time. They all have a shelf life because the cross-linking goes forward even at lower temperatures. So we put these in a refrigerator, and then we pull them out as we need them, and we can lay those in place. So now we have resin and the fibers in the mold when we lay it up. So the interesting thing about this is that we can get as much as typically, I guess, around 60% volume of fiber as versus matrix in our material. And we can't do that can't even approach that using the wet layup method. So the next step in the process, once we get the fabric and the resin into the mold, is to debulk or consolidate the part. And I mentioned a vacuum bag before in the overall process. This is the vacuum bagging process. And so you see a cutaway here. This is the tool or the mold wall down at the very bottom. And then on top of that, we have a release coat or a film that allows us to remove the part, the composite laminate, from the mold. And then we have a peel ply here. And this peel ply, as you saw in the video, gives us surface quality and allows an extra release here from the mold and the components around it. On top of that, we have a porous release paper, which allows us, this gives us a surface to press down on the part, and it also allows gases and resin to escape because of the porosity. Then we have a breather material, more porous, allows gases and resin to escape. A barrier release, which is a seal, if you will. Then a bleeder material that allows us to get rid of excess resin, and finally the vacuum bag itself. We have a fitting here that allows us to pull vacuum out. This is the fitting that you see, and we have sealant tape all around. So it's a fairly simple process in concept. It requires some practice and some artistry to be able to put all the parts together and effectively make this work. And in the student activities, I'm going to have you take a look at some videos of setting up the vacuum bagging process. So once we get it bagged, we need to raise the temperature in order to facilitate our cross-linking. Now, as we pull a vacuum, we're putting pressure on the top of the fabric and pressing it down into the mold or consolidating the part. So for normal parts, that is not very high performance parts, structural parts, we can sometimes get by with an oven cure. So this is not a pressurized oven. This is just a normal industrial oven. And we take the vacuum bag part, we put it in this oven, and we soak it at temperature to get the cross-linking going. These ovens are characterized by fairly low temperatures, 200, 250 degrees Fahrenheit, and they are at ambient pressure. So, what's the next step up? Well, if we want really high performance parts, that is, we need to be sure that we have consolidated well the parts, then we need to go to an autoclave. And the autoclave is essentially a pressure vessel. It's been described as a big pipe bomb. So it's a pressure vessel. We can increase pressure say with 200 psi on the inside of this thing. We have a vacuum bag also, so the vacuum bag pulls some pressure on the outside of the part, pushing it into the mold, and then we have an external pressure, positive pressure on top of the vacuum bag that increases the force pushing the fabric into the mold and also pushing out any air bubbles or gas bubbles and excess resin that we have. So this is an overall schematic of the plumbing and the autoclave. This, the smaller autoclave down at the bottom, I believe is at the Cessna plant in Wichita, Kansas. This larger one is in Wichita, but it was designed and manufactured specifically for making parts for the Boeing 787 fuselage, big parts. This is a typical autoclave cycle, so you can see we bring the temperature up in steps so that we can get it up to, in this case, 350 degrees. It's fairly typical for an autoclave part. And we also can bring the pressure up, and in this case we have the pressure, external pressure, at about 80 psi. And this is the time cycle. It has to sit in the autoclave to cure. So you can see that when we make the part, we invest all this time and labor in putting the part together, and then we spend 8 hours in the autoclave, and then we know if we've got a good part. So it's important that you control the process in making composite parts at every stage as you go through manufacturing this part, because you're adding a lot of cost into the part as you go along. This is a little different take. This is a spin-off on wet layup. This is called a vacuum resin infusion process, and it's becoming very popular. The reason is it allows you some of the advantages of pre-preg without the expense and the hassle of having to buy pre-impregnated materials and having to store them under refrigeration. What this allows you to do is to lay the resin, or lay the fibers, the cloth or mat, into a mold, set up your vacuum bag, and instead of just pulling a vacuum to press the part into the mold, your vacuum bag also gives you a vehicle to pull resin. You have a resin reservoir here and a hose going in from one side of your part. On the other side of your part, you have a vacuum hose that goes out to a vacuum pump. And so as you start pulling a vacuum, you pull this vacuum bag down onto the part, pressing the part into the mold, and at the same time we suck resin up through the fabric underneath the vacuum bag and out this side. So this is becoming popular with aerospace manufacturers because it cuts out some of the hassle involved in using a pre-preg. Now you can see from all of these, though, the bulk of the labor, the cost in the part so far is in this layup. You know, how do you, everything we talked about so far is you've had a person going in and manually putting these layers in place. This is a slow, time-consuming, expensive, labor-intensive process. And it's human beings tend to not do repetitive process real well. So if you've got a dull and boring process that's repetitive, you're going to end up having some human error built into that. And once since we're using the process control for our quality control, our main quality control here in these parts, that's not a good thing. So how do we get rid of some of that labor involved in laying up these parts? Well, there's a lot of effort going into automated layup. Just as in assembly we talked about automated assembly and the reasons for doing that, same deal applies in automated layup. So these are a couple of machines. These are automated tape dispensing machines. So we have a pre-preg tape, and you can see the head here is running back and forth across the mold, laying down tape, and we can use it, and this is essentially a 6-axis robot that's driving this thing. This is a gantry style robot that's allowing us to go in the XY direction and up and down so that we can conform with the mold here. And it has a tape laying head on it. Much like a tape dispenser for packaging tape, most everybody's seen those, where you have a roll and you pull this roll along and it lays the tape down. Well, this is an automated, more highly controlled version of that. So this is toe placement as opposed to tape placement. Toe placement, we're going to have typically a mandrel, that is a male mold. You can see the male mold here. This male mold is tied into a device similar to a lathe, so that it rotates this mandrel or male mold, and then we can lay the toe across the top of it. Now remember, a toe is maybe 1,000 strands twisted together of carbon fiber. So as we rotate this mandrel, we can move the orientation of our dispensing head, and we get a different angle of the fiber with respect to the long axis of the mandrel. How do you keep the fiber in place when you lay it down? Well, the fiber is typically wetted, or the toe is typically wetted with a small amount of resin that makes it tacky, and it kind of holds it together. Once you get the part made, then you bag all this up and you either use a vacuum infusion or wet layup or whatever method you want to get the resin, the remainder of the resin in, and then you go through the curing process as we talked before. I want to show you a video of some automated layup using or building the Boeing 787.
The 787 will be built differently than any other airplane that Boeing has ever built. Instead of being made from metal, it's made from carbon composites, and what we're seeing here are the heads of the machines that lay down the tape. Carbon tape it comes in rolls like duct tape, is rolled along a surface and laid flat. The carbon fiber is infused with epoxy resin, and this black material on top of this slab is what's being laid. And when they're making a fuselage, they spin a barrel. This is called a mandrel. It's a cylindrical mold, and they lay the tape. There's the tape head machine again, laying the tape in layers one after the other as the mandrel spins and the fuselage takes shape. You can see it turning as the head works its way along. And so they make layers of tape, and when they've got the shape ready, they put it in a giant oven. That's what this is. It's called an autoclave. They've had to build some of the biggest autoclaves in the world for the 787 project. The one in Wichita, for example, is 30 feet in diameter, 70 feet long. They take it out and it's baked hard. The material is black when it's not painted, so you'll see airplanes no longer having the shiny metal unpainted surface. Joining two of the fuselage pieces together, and there we have the beginning of a Dreamliner.
Okay, so this is the high dexterity tape placement head. You saw some of that on the film, on the video that we just looked at, and this is the end of that, or the end effector on that head. Again, it's a gantry. This particular one's a gantry style robot with this head on the end of it. We also have devices that can do variable angle ply lamination if we're laying up sheets apart or sheets for parts. We can lay in various angles on this automatically by arranging a set of conveyors so that it lays the tape or fabric down. This is the part of a fuselage of a rocket. So this is a composite part, kind of similar to the Boeing fuselage that we looked at. So future directions for composites, more automation, and we're going to talk about that in some of the manufacturing stuff in modules 7 and 8. Embedded sensors and actuators, we talked about that before. There's a couple of interesting wrinkles on this. We're actually embedding RFID sorts of tags inside composite aircraft parts now. So what this allows us to do is to use this radio frequency identification tag to record some of the manufacturing process parameters for that particular part numbers, some other interesting things that allow us to store and handle that part. And also we can embed things like strain gauges to look at what the stress history of that part has been. So we can that allows us to plan out maintenance or replacement of parts. Well, that wraps up our introduction to composites. From here, we're going to go into more detail on the composites manufacturing in modules 7 and 8. And then in modules 9 and 10, we're going to talk about some ways that you can actually have your students get hands-on with composite materials. Some projects, if you will, and how you might do that. So anyway, that's it for today. Thanks.